Welcome dear grade 11 students to these videos concerning or about training exercises about quadratic equations. Of course, I'm not going to explain about quadratic equations. I'll just make a little revision or a quick revision for them concerning the delta and the general form of the quadratic equation. If you want more explanations, you can view the videos about explaining quadratic equations and how to deal with quadratic equations. Here we have the general form of the quadratic equation, which is ax squared plus bx and plus c equals to 0. We are going to use delta, which is equal to b squared minus 4ac, and according to delta we are going to know if the quadratic equation has two real distinct roots, if it doesn't have any roots, and if it has a double root. So if delta is positive, let's remember the equation has two real distinct roots. If delta equals to 0, the equation has one double root, and if delta is less than 0, then there are no real roots. Okay, so let's get started with the first training exercise, and we are going to use quadratic equations in these exercises in order to talk about higher level ideas and to solve higher level questions. Consider this equation: x squared minus 7x plus 12 equals to 0. The first question is to show that e has two distinct real roots, x prime and x double prime. And for the second part, we have to suppose that these roots, x prime and x double prime, are the sides of a right triangle. We have to find its hypotenuse. So, first of all, to show that e has two real distinct roots, I should prove that delta is greater than 0. So, let's go ahead and show that delta is greater than 0. This is the equation. As I told you, delta is equal to b squared minus 4a, which is 1. So a is 1, b is minus 7, and c is 12. Applying delta, b squared means minus 7 squared. Then the minus will be removed because we are going to make it a power 2. Minus 4 a c. A is 1 and c is 12. Thus, we got 49 minus 48, and it is equal to 1, which is a totally positive number. Thus, delta has, thus this equation has two real distinct roots. That's according to the first part. Now, according to the second part, we suppose that this is our figure, that these two roots are like the sides of right triangle. They present the sides of a right triangle, and surely they are positive. X prime and x double prime, we need to calculate the hypotenuse of this triangle. According to Pythagoras, because we have a right triangle, we have to directly think of Pythagoras. It says that the hypotenuse squared is equal to x prime squared plus x double prime squared. That side squared and that side squared. That's Pythagoras theorem. Now, x squared plus x double prime squared, if you remember, we have that rule that says if x plus y squared is equal to x squared plus 2xy plus y squared. You have that rule. All of us know it. Now, if I need x squared and y squared alone, like x prime squared and x double prime squared alone, I just move 2xy to that side here, and thus I will get that x squared plus y squared is equal to s squared minus 2xy means 2p. Why is it s squared minus 2p? Because we have to know that s is the sum of the roots. It's x prime plus x double prime, and p is their product. which is x prime times x double prime, and thus whenever we see x prime squared plus x double prime squared, it's directly s squared minus 2p, as I just proved it just right now. So s squared minus 2p, then all what I have to do is to evaluate s and p. Now what is s and what is p? According to another rule, s, let's review, s is equal to minus b over a, and p, the product, is equal to c over a, and that's also proved in the explanation videos. Now according to this equation, b is equal to minus 7, thus s is equal to minus 7, so s is going to be equal minus 7 over a, which is 1, and thus s is equal to 7. For p, it is c, which is 12 over a, and thus p is equal to 12. And thus to evaluate this, s squared means 7 squared, which is 49, minus 2 into p minus 2 into 12, which is 49 minus 40 minus 24, and 49 minus 24 is equal to 25. Thus hypotenuse squared is equal to 25, then the hypotenuse is surely the radical of 25, which is 5. And thus we found the measurement of the hypotenuse of this right triangle, and probably that side is equal to 4 and that side is equal to 3, and that's our hypotenuse 5, and this is the most famous right triangle whose sides are 3, 4, 5. That's according to the first training exercise. Let's move to the second one. In this training exercise, we have this equation, x squared minus 5x plus 4 equals to 0. We have to show also that e has two real distinct roots, and without finding the roots, we have to calculate these values. 1 over x prime plus 1 over x double prime, 3x prime into x double prime squared plus 3x prime squared into x double prime, and x prime power 4 minus x double prime power 4 over x prime minus x double prime. Note here, I can safely put x prime minus x double prime because x prime and x double prime are distinct. So x prime minus x double prime will never be 0, and that's safe to be written like this. Okay, so x prime minus x double prime will never be 0 because they are distinct roots, and distinct roots are not equal, so their difference is never 0. So let's go ahead and see how to solve this. Again and again, whenever we have to show that e has two real distinct roots, we have to go to delta to calculate delta and prove it positive. So first of all, delta is equal to b squared, which is minus 5 squared, minus 4 into a, which is 1, and c, which is 4. Then delta is 25 minus 16, which is 9. Then 9 is positive, so e has two real distinct roots. Now let's start with the first one, and notice here I just wrote s is equal to 5 and p is equal to 4, applying the rule of s equals minus b over a, where b is minus 5, then minus 5 into 1 is 5, and p is c over a, which is 1, so it is 4. I wrote s and p and prepared them because I'm definitely going to use them in calculating these values. For example, 1 over x prime plus 1 over x double prime will be, when I make the same denominator, that's surely what I should do. So here I have to multiply by x double prime up and down, and here I have to multiply by x prime also up and down. So I will get x double prime or x prime, whatever, they are commutative. Addition is commutative, so I can exchange x prime or x double prime plus x double prime over the product x prime dot x double prime. That is the sum. So as we said, that's the sum and that's the product. So s over p. That value is equal to s over p, where s is 5 and p is 4. So definitely 1 over x prime plus 1 over x double prime is the sum over the product, which is 5 over 4. And we are done with that one. Let's move to the second one. 3x prime x double prime squared plus 3x prime squared into x double prime. As you noticed, there is a common factor here, here, and here. So I can take 3 as a common factor. I can take x prime and I can take x double prime. So we take common factors 3x prime, x double prime, and what remains inside is just 1x double prime and 1x prime. So again and again, we get 3p, that's the product. Whenever we see x prime dot x double prime, that's the product. And here we have s, the sum, x double prime plus x prime. So we got 3ps, so 3 into 4 into 5, which is 60. That's according to the second one. Let's move to the third one, which is x prime power 4 minus x double prime power 4 over x prime minus x double prime. According to that one, that's an identity. Whenever we see an even power here, for example, and minus in the middle, we think of the identity that looks like the difference of two squares. So x prime squared minus x double prime squared into x prime squared plus x double prime squared. Now, according to that one, that's again an identity, and I can factorize it more and more. So we got x prime minus x double prime into x prime plus x double prime, and this is kept without any factorization because there is plus in the middle. Now, I can cancel this with this, and I'm sure that the value I'm canceling is not equal to 0 because they are distinct roots. Then definitely they are not equal, so the difference is never 0. What remains is that one into that one. That's s squared minus 2p, as I just mentioned in the previous slide, and that's s. So we got s into s squared minus 2p. So again, whenever I see x prime squared plus x double prime squared, it's the rule that says that's equal to s squared minus 2p. And thus s into s squared minus 2p is 5 into 25, because s squared is 25, minus 2 into 4 minus 8. That's 17. Or we can use the calculator, like 5 into 25 minus 8, and here is the answer. It is 85. So that's according to this training exercise. In this slide, we suppose that x prime and x double prime, the roots of the previous equation, are the abscissas of the points A and B respectively. So as if we have 2 points, A is of abscissa x prime along the x-axis, for example, and B is of abscissa x double prime. We have to find the abscissa of M, where M is the midpoint of segment AB. So as all of us know, whenever we have a midpoint for a segment, okay, the abscissa of the midpoint is, for example, if we have here A and here B, and the middle point or the midpoint is M, then xm is equal to xa plus xb over 2. That's the rule for the abscissa. So xm is equal to x prime plus x double prime over 2, where x prime is for A and x double prime is for B. But x prime and x double prime is S, so the final answer is that xm is 5 over 2, because S, as we mentioned before, S equals to 5 using the previous slides, and 5 divided by 2 is 2.5. Thank you, and inshallah we'll meet in